Okay, here we are again, and this time we're going to go through or get started on alternating current circuits. Okay, uh, alternating DC circuits are pretty simple. Okay, by now, but uh, we always use DC circuits mostly because of the way that they can produce power. Okay. But one thing we haven't looked at right now is we looked at the circuits having a voltage source or some kind of a voltage source, such as a battery or a power supply, and with a bunch of resistors and some tied together somehow to give you current that only flows in one direction and goes through all these resistors and basically reduces the voltage from the input voltage by voltage drops across each of the resistors. And that current is always constant in time, does not vary at all. But all that changes when we go to alternating current. Now, how did we come upon alternating current? Well, it all really started when somebody noticed that passing current through a wire creates magnetism. Okay, just the just passing a DC current through a coil of wire will get you a permanent magnet, or what we call an electromagnet. Okay, so there is something between the movement of electrons. The current is movement of electrons and a magnetic field, that they're associated with one another somehow. And in fact, it's a reversible process in that we find out that if we pass a conductor that contains free electrons that are free to move, and we move it in a specific direction and cross it across a magnetic field, we get current, which is the opposite effect of when we get current going through a wire, and if we change it, we get a changing magnetic field across that wire. So it's a reversible process. All right. So it all has to do actually with a velocity vector and a magnetic vector. Those two vectors, when they cross each other, okay, we do mathematically, we call that a cross product. And the result of that cross product of those two vectors is that you get a third vector that's perpendicular to both of those vectors. So if you're talking about a wire moving at a velocity across a magnetic field with a magnetic field vector, you get a result of a current velocity in the opposite, in a perpendicular direction, perpendicular to both the magnetic field and the movement of the wire. All right. So, but when we get into analyzing AC circuits basically are pretty much like DC circuits, but with the fact that in an AC circuit, the current runs first in one direction, then goes back in the other direction. So if it goes in one direction, it will come back and do the other. It goes seesaws back and forth. Okay, and that's what we call alternating current. And because it alternates like that, then there's a change in the magnetic field that it produces. And there's also a change in the voltage that it produces, okay, when you pass it through a resistor. So the two major components that we're going to add now to AC circuit is first we're going to look at a capacitor, and then we'll look at the inductor. And the inductor can be just a simple inductor, or it could be a transformer. Transformer basically is a couple of inductors put together. All right, and that'll be interesting. But the big thing about AC circuits is that they are time dependent. Okay, whereas in DC circuits they're not time dependent. Okay, there's no timing in a DC circuit. The current is and the voltage are constant. Okay, but in a AC circuit, those things change. The voltage and the current changes with time. And because they change with time, then the current or the voltage has to be specified both as a magnitude quantity, but also it has a timing quantity, which we call a phase. Okay, so because it has two components, then we can treat it like it was a vector. It's not really a vector, but it has the feelings of a vector. It has a magnitude and has an angle. Okay, in this case, it has a current magnitude or a voltage magnitude and a phase angle. Okay, so we will notice then by next week that we can actually use vector algebra to analyze AC circuits. Okay, and because of all these changes that occur, the AC circuit is far superior to DC circuits. Without AC circuits, we wouldn't have radio. We wouldn't have television. We wouldn't have a lot of the devices that we have today. Okay. Before 1917, all houses were supplied with electricity, used DC electricity. Okay. So that DC was good for lighting up a bulb and maybe doing a few other things. But the distribution of the voltage using DC was not good. Okay, there were always a lot of losses. But in early 19th century, a person came up with a method of alternating that current. Okay. And by alternating that current, he was able to create a much more efficient system of distributing voltages to all households, because you could use a transformer. So you don't need only 125 volts. Okay, you could get 240 volts and higher, lower, whatever. You get all different ranges of voltage that could be distributed by simply using a transformer. All right. So that's the beauty of AC circuits. And we'll get started first by looking at some of the math today and considering magnetism and current flow, DC current flow through a wire that creates a magnetism. So, but before, like I said, before 1970, what happened in 1917 was what they call current wars, okay? Because before then, Mr. Thomas Edison, was famous for DC currents. He believed in DC currents, and that was the end of it, okay? But along came this Slavic person, Tesla, okay? Mr. Tesla came out with AC circuits, AC currents, and in 1917 they had a contest. That contest was actually won, not immediately, but by Mr. Tesla. Okay, Mr. Tesla proved that it was so much more efficient to have AC circuits rather than DC circuits. And so after 1917, then there was no matter what part of the country at some different parts of the country had DC circuits and other more advanced parts of the country had AC circuits. Okay, and then AC took over. So we are now using AC circuits in our homes. So let's get started. We'll get started with our first day work. And the first day work has a homework assignment that I don't expect too many people to get. Okay, but make an attempt to get it. So basically, we're trying to create a math for currents. All right. So let's get to it.